Assalamu alaikum friends. I'm Taqdees Siddiqui with Computer Graphics for Bachelor's in Computer Science students, the course being offered by Virtual University, Government of Pakistan. We have started our odyssey into 3D graphics, and this exciting journey is on. We're going to continue further today. Today is our 21st lecture, and let's see what we have today. I promise that we are going to have something more interesting today. So we'll be talking about triangles and planes. And what kind of triangles are we going to talk about? Let's see. So, shall we begin? We're going to start with triangles. We are very much comfortable with the concept of a triangle, a regular polygon with 3 vertices, all connected with straight lines. That's what forms a triangle. Triangles have the same role or importance in 3-dimensional graphics as is that of a point or a pixel in 2-dimensional graphics. So, today we are going to talk about this important role that they play in 3D graphics. In every PC, the hardware that is coming now that supports accelerated graphics is making use of this very concept of dividing surfaces into multiple triangles in order to render objects in a beautiful manner. They are really very powerful tool. Although there are certain other primitives that can also be made use of, and actually when we are talking about hardware implementation, there are trapezoids that are being used, but nevertheless the basic concept is that of the triangles. And these triangles help us make our solid surfaces in such a manner that we are able to fill them up in realistic manner. We are able to come up with realistic views of 3-dimensional objects and surfaces. So, when we draw a polygon, you are comfortable with the concept of a polygon as well. A polygon can actually be defined or drawn as a series of triangles. Triangles can be put together to come up with a polygon. Hardware devices actually make use of fan of triangles. A fan of triangles, yes, we are going to talk about this concept a little while after. You will be able to see how we can make fans of triangles represent polygons. The triangles flesh out a 3-dimensional object, connecting them together to form a skin or a mesh that defines the boundary surface of an object. So as I said earlier, any solid object that has a definite surface that needs to be shown can be divided into multiple of triangles in order to come up with a mesh or a skin-like effect. That skin, which has varying light deflection effects, is accomplished by virtue of making using of the triangles. Multiple triangles allow us to deal with each part of the surface differently, and we are able to fill them up with a different texture or with a different tinge or with a different light. So, this exciting journey is going to be with triangles making up the surfaces of 3-dimensional objects. Typically, the ordering of the vertices of triangles that make up these surfaces goes in a clockwise fashion. So, we start with the first one, the second and the third in a clockwise manner, and then whenever required we are able to join multiple triangles together and form a greater part of the surface. This illustration on your screens right now explains what we mean by the clockwise winding order of the vertices. The top vertex you can see marked as the 0, then the bottom right, which is marked as 1, followed by the third vertex marked as vertex 2. So from 0 to 1 to 2, the order that we are traversing these vertices is a clockwise order, and hence is called a clockwise winding order whenever we are describing or specifying any of these triangles that we would be making use of in order to define or compose the skin or surface of our three-dimensional objects. In this particular example, you can see that the point 0 has got its coordinates minus 1.0, 3.0, and 0.0. Point 1 is specified as 3.0, minus 2.0, 0.0, and point 2 is minus 2.0, minus 3.0, and 0.0. Just reminding that since we are talking about three-dimensional space, we are allowed to have these triangles poised in any manner. So we may have some triangles that are lying in xy plane or xz plane, or for that matter yz plane, but we can also have any other orientation for these triangles. But something very peculiar about the triangle is that when we have three vertices defining this picture called the triangle, we are bound to live in a single plane. We are going to define plane and its implications in detail shortly as well, but this is an interesting thing to notice about the triangle. Another aspect that we need to concentrate on is that when we are living in a three-dimensional space and we are defining certain object surfaces with the help of these triangles, there would be certain triangles that would be visible and there would be certain others that would not be visible. So in order to have this fact established that which part of the surface is actually facing us the viewers, from where the camera is looking into the object or into the scene, we have to know what part of the surface formed by the triangles is visible and what part is invisible. We are going to formally talk about these methods of detection of hidden surfaces or the visible surfaces, but the basic idea we can float right now, and that is that we should have a dot product between the normal of the plane that contains our triangle with the vector that is originating from the very point that we are viewing the scene from, which is the camera, and that results in specific values that indicate whether this particular triangle is in the visible area of the object or not. Right? So if we come across some triangle which is in the visible area, that would definitely be shown. And if we come up with a result that indicates that the triangle is actually an invisible one, is facing away from us, the triangles or the parts of the surfaces that would be facing away from us, that would always be hidden whenever we are talking about solid objects, that is. So sure, anything that is to be hidden, that would not be rendered to become part of the scene. Anything that is on the surface and is facing the camera, that would actually be shown or drawn in the scene, and hence would be taken care of. Calculations ऐसे ऑब्जेक्ट के लिए और ऐसे पार्ट ऑफ ऑब्जेक्ट के लिए जो कि हमारे सामने ही नहीं है, जिसको दिखाना ही नहीं है हमें, वो तो फिर मीनिंगलेस है. We don't need to do that. So we'll save and conserve energies and our computation power, and would only concentrate on the front part, the area of the surface. In this, I'm making use of the word triangle in place of the surface, because we have already said that skin or the surface of the object is composed of triangles. So the triangles that are visible, they would be rendered and shown. The triangles which are hidden, which are not facing the camera, which are behind the scenes, they would naturally be kept out of the calculations. Now we can take a look at the code that defines triangle with the help of structure and the concept of a public constructor. You can look at the code right now, the structured triangle with an array of size 3. Now this array is going to hold the values of the vertices of the triangle, and you can see down below the function triangle with the arguments type v0, type v1, and type v2, the three vertices of the defined type. And what we do is we take these values and place them in our array. So you can clearly see v of 0, the first location of that array, is going to hold v0, the first vertex. V of 1 would be holding V1, the second vertex, and V of 2 would be holding V2, the third and the last vertex of the triangle. So the triangle with all its vertices would be stored in this array, a typical method of storing, because programmatically we see that processing of arrays is quite easy. That makes our life easy whenever we have multiple values to crunch in a specific order or manner. So that's why we will be making use of the concept of array to hold vertices values. The next is our topic about the triangle strips or meshes. This is what we initially mentioned, that whenever we have a three-dimensional object, the surface of the object would be subdivided into multiple triangles, and these multiple triangles would be close together with each other in order to form the concept of the skin. Now that is established or achieved using the concept of a triangle strip or a triangle mesh. We have multiple triangles joining hands together and forming part of a surface. There are three different methods of generally representing lists of triangles. In fact, indirectly we have talked about the first such method, which means that using an array to hold the values of the vertices of the triangle. So if we've got many triangles, we can use a triangle list to represent them. हर एक ट्राइंगल के 3 वर्टेक्स जो हैं उनको हम अरे के अंदर स्टोर कर लेंगे, और इसी तरह से दूसरी ट्राइंगल के तीनों वर्टेक्स, तीसरी के, चौथी के, so on and so forth up to n we can go. All 3 vertices of each triangle would be stored as elements of an array. But this is the most simple method, but is not very efficient in terms of memory. There are 2 more methods that actually are more efficient than this one, and those are making use of the concept of a fan, a triangle fan, or a triangle strip or a triangle mesh. Triangle fan और triangle strips जो हैं वो vertices of successive triangles को आपस में share करते हैं. In a different manner of course, हम इन दोनों को अभी बारी बारी देख लेते हैं कि किस तरीके से हम ट्राइंगल फैंस के ज़रिए से और ट्राइंगल मैशेस के ज़रिए से मल्टीपल ट्राइंगल्स के डेटा को स्टोर कर सकते हैं और होल्ड कर सकते हैं. First we talk about the triangle fans. The triangle fans conceptually look like the folding fans that we see in ordinary souvenir shops, typically the Chinese fans that we see. You fold them together to form maybe a columnar strip or stick-like form, and if you open them, the fins of the fan, they just fan out and make one contiguous picture, a fan. Typically, some traditional pictures are also drawn on those parts of the fan, which when fanned together, they form the complete whole picture. So that very idea is made use of in triangle fans. And you can very, very easily physically perceive what a fan of that kind look like. All parts of that fan have one hinging point where a rivet actually puts them together and keeps them together at one end. The other ends are free, and that is why we open the fins of the fan and make one contiguous picture. That very idea is utilized for representing multiple triangles as well. And now we'll see how this fan will help us define any polygon. A typical polygon can very easily be conceptually and physically divided into these multiple triangles. In this particular picture that you are seeing right now, all the triangles that are forming this polygon are sharing one vertex, and that shared vertex is the point 0. Vertex 0 on the top, that is a shared one, and you can start from the right hand side and start counting how many triangles we've got defining this polygon. So here we have 0, 1, 2 defining the first of the triangles, then 0, 2, 3 is defining the second one, second contiguous triangle with having a common vertex at 0. 0, 3, 4 is defining the third one. 0, 4, 5 is giving the fourth one. So in this fashion, this given polygon is divided into multiple triangles with one shared point, 0, as the shared vertex. So any n-sized polygon can be represented very efficiently using a triangle fan. The other idea, that is that of triangle strips. In this case, we have seen in fans that we have one hinging point, which is a common one amongst all the triangles defining the given polygon. But in case of a mesh or a strip, what we'll do is we'll not have one common point. We will be having multiple shared vertices amongst consecutive triangles. Let's take a look at that. Triangles in a triangle strip, instead of sharing a common element with all other triangles like a fan, only share elements with the triangle immediately preceding them. The first three elements, of course, they have to be defined. The first three elements of the given triangle that starts our triangle strip or mesh, they will have to be defined. For instance, we are starting with 0, 1, 2. So the 0, 1, 2, they will be stored as the definition for the vertices of the first of the triangles in the strip. For the second consecutive triangle, what we'll do is we'll make use of two of these vertices as the vertices for the next triangle, and the third vertex for that next triangle would only be added as the new one. Now, whichever that third one is would actually decide that which of the existing two shared vertices of the triangle would be shared for the third one. But nevertheless, the concept is that we have one edge of a given triangle common with the next triangle that defines part of the mesh. We'll be able to take a look at an actual picture of a strip in order to make a better view or better idea of the same. So, whenever we have a strip of triangles, then we are going to conserve more space. You'll actually be noticing that in case of a fan, we had only one vertex which was being shared by all the triangles forming the fan. But in case of a strip, हमारे पास हर एक triangle के दो vertex अगली triangle के साथ इस्तेमाल हो रहे हैं. So we are conserving more space, most definitely. So पहली triangle के vertex बताते हुए तो हमें तीनों इस्तेमाल करना ही पड़ेंगे, because 0, 1, 2 would be required in order to form the first one. लेकिन उसके बाद maybe we drop the 0 out, 1 and 2 would be shared vertices for the third triangle, and only the vertex number 3 would be added. उससे अगली triangle के अंदर फिर 2 of the preceding one would be shared and only one new would be added. This idea can be explained further with the help of a picture, and let's take a look at that one. Now you are looking at a triangle strip. Now this one starts at the left end and we are extending it towards right. So you see the vertex 0, which is the starting one, followed by 1 and 2. 0, 1, 2. These first three vertices are defining the first triangle. But for the second one, we make use of vertex 1 and 2, which is already existing as part of the triangle 1 definition, for triangle 2's definition. And we only add vertex 3, which helps us make this second contiguous triangle, which is sharing one edge with the first triangle. इसी तरह से अगर आप second triangle को देखिए तो उसके जो vertex 2 और 3 हैं, they are being shared by the third triangle, और सिर्फ vertex 4 add करके हम तीसरी triangle जो है वो भी बना लेते हैं और define कर लेते हैं. और इसी तरह से चौथी triangle जो है उसमें vertex 3 और 4 share हो रहे हैं, और सिर्फ vertex 5 के addition से we have defined yet another triangle. So in this manner we can define a skin or a surface as a strip or mesh of triangles. So if you look at the picture without the triangle concept in there, it is looking like just another polygon. Well, yet another polygon defined using the concept of strip of triangles. Now, how do these strips of triangles help us in conserving energy, in terms of conserving space? We'll be able to notice that. Next thing that we need to talk about is the concept of a plane. We have visited the concept of plane already as well, because when we were talking about two-dimensional graphics, we were talking about the XY plane. So we do have that idea that a plane can represent certain primitives and is unable to represent certain other graphic primitives. But we do have this concept in three-dimensional graphics as well. It is very much important because we have already said that a triangle, by its definition, cannot fall in more than one plane. So it has to be in one plane. All the three vertices, they will be coplanar in order to accomplish the definition of a triangle. Planes are to three-dimensional graphics what lines are to two-dimensional graphics. वही कॉन्सेप्ट जो 2D के अंदर लाइंस के जरिए से था वही यहाँ पर हमें प्लेन्स के जरिए से मिलेगा, बिकॉज लाइंस वहाँ पर हमें दो डायमेंशंस इस्तेमाल करती हुई दिखाई दे रही थी. फ्रॉम पॉइंट टू पॉइंट वी कुड ड्रॉ थिंग्स एंड द लाइन was composed of pixels that were connecting two points using the shortest possible distance covered between the two, shortest possible path between the two. Here we do have the concept of triangles used as defining surfaces of three-dimensional objects, and each of those triangles would be existing in a plane. Therefore, we'll be making use of multiple planes when we'll be talking about defining a surface or skin of a three-dimensional object. The planes are n-1 dimensional hyperplanes that can help us accomplish various tasks. As I said, we are living in the three-dimensional graphics world, so our planes would be the 2D planes. Planes are defined as infinitely large, infinitely thin slices of space, like big pieces of paper. Just to help you conceive the idea, perceive it, that we can imagine that a plane is like a large piece of paper, infinitely thin slice of space. Infinitely thin slice because we are not concerned with the thickness of a plane. We are not going to have any movement, any transformation of an object within the boundaries of the plane. The plane itself would actually be giving us, like a mirror, a surface to show things, a surface to represent certain things which exist in a single plane, a single two-dimensional plane, to be specific in our case. Each of the triangles that make up our model, they exist in their own plane. This we have already said कि हर एक ट्राइंगल जो है बाय डेफिनेशन उसके तीनों वर्टेक्स जो हैं वो कोप्लानर होंगे तो वो ट्राइंगल की डेफिनेशन पे पूरी उतरती है. लेकिन जब हमने ये कहा कि किसी भी सॉलिड ऑब्जेक्ट की सरफेस को हम मल्टीपल ट्राइंगल्स में डिवाइड करने जा रहे हैं, तो इसका मतलब तो ये होगा ना कि वो ट्राइंगल्स एक दूसरे के साथ जुड़ी हुई होने के बावजूद उनके प्लेन्स मुख्तलिफ हो सकते हैं. बिकॉज जरूरी नहीं कि हमारा ऑब्जेक्ट जो है वो फ्रंट ऑफ अ क्यूब ही हो. इट कुड बी अ सफेयर. अगर आप सफेयर की सरफेस को इमेजिन करें कि आप उसको स्ट्रिप ऑफ ट्राइंगल्स में डिवाइड कर रहे हैं, तो एवरी ट्राइंगल ऑन द सरफेस would be existing in a different plane from the every next triangle. भले वो एक दूसरे के साथ contiguous ही क्यों ना हो, but still there is room that two consecutive triangles of a strip would be existing in two different planes. We can well imagine that, right? When we have a plane that represents a slice of three-dimensional space, we can perform operations like classification of points, polygons, and clipping. We have talked about this very concept, that what kind of primitives can be defined in 2D planes. So whenever our three-dimensional space is divided into two-dimensional planes, each of those planes will have its own limitations, will be able to define only certain primitives in that plane. But since we are talking about multiple of those planes existing or coexisting in the three-dimensional space, the same concept that we have visited in 2D would be actually coming into play for 3D graphics as well. In case of three-dimensional graphics, we'll be actually making use of multiple of two-dimensional planes in order to accomplish what we used to accomplish in single two-dimensional plane in 2D graphics. So 3D graphics actually becomes an extension of the 2D graphics. कि आपने decompose कर लिया है उसको into what you have already conquered and you have understood. फॉर इंस्टेंस हम पहले ही जानते हैं कि किस तरीके से हम टू डायमेंशनल पॉलीगॉन्स को फिल कर सकते हैं. तो अगर 2 डायमेंशनल पॉलीगॉन फिलिंग हमें आती है और हम 3 डायमेंशन में अपनी डिफाइन की हुई किसी भी सरफेस को एज स्ट्रिप्स ऑफ ट्राइंगल्स एज पॉलीगॉन्स दिखा रहे हैं, तो हम उसको अलग अलग फिल करने की सलाहियत तो रखते ही हैं, राइट? So we'll be able to accomplish the same task over here in 3 dimension as well. We'll be able to give our objects a 3-dimensional look by virtue of making multiple of those 2-dimensional planes, which would be holding, each of which would be holding a triangle, which actually is defining the surface of the 3D object. Interesting, isn't it? It really is going to become very easy once we conquer the basic concept. So the question is, how do we represent planes? We are looking at an equation that defines a plane. Ax plus by plus cz plus d is equal to 0. That is an equation that defines a plane in 3D. Now over here in ax plus by plus cz plus d is equal to 0, we have the triplet ABC, which is representing what is called the normal of the plane. I hope I don't have to stress very hard on this concept because you've already established this concept. What is the normal to a plane? Yes, the vector that is making 90 degrees angle outward from that plane. So the triplet over here in this equation composed of A, B and C is representing the normal of the plane. A normal is a unit vector that conceptually speaking sticks directly out of a plane. A stronger mathematical definition would be that the normal is a vector that is perpendicular to all of the points that lie in the plane. As I said, in case of a triangle, all 3 vertices exist or coexist in the same plane. Now that very idea is actually being stretched a little further, that if we have a normal to that triangle, that normal would not only be normal to that triangle but also to all the points that lie in that plane, because there are going to be innumerable points in that plane. Because concept जो है हमारा theoretically speaking वो तो यही है ना कि slice of 3D space which is infinitely thin and infinitely large. So all the points that exist in that plane, उन सब के ऊपर जो normal to that plane है वो 90 degrees का angle बना रहा है. It is perpendicular to all those points. The D component over here in this equation is actually representing the distance from the plane to the origin. So if we have our plane existing at x distance away from the origin, that distance would be actually given by this component D. Depending upon where our plane exists, this D would be positive or negative. But अगर हमारा प्लेन इस तरह से poised हो कि वो origin में से ही गुजर रहा है, तो फिर D की वैल्यू क्या होगी? Naturally, it's got to be 0 because it would not be away from the origin, it would be going through the origin. Origin would itself be part of that plane. So we can always compute this distance by tracing a line towards the plane until we hit it. We start from the origin and we draw a line towards the plane, and as soon as we hit the plane we know that okay, we have reached the plane. The distance covered from the origin to that point would be the distance of that plane from the origin, which is in this equation represented as D. Now finally, the triplet x, y, z is any point that satisfies the equation. And what points would satisfy this equation, do you think? Sure, any and every point that lies in that plane, that would be satisfying this equation. So अगर हम अपनी ट्राइंगल्स के एतबार से बात कर रहे हो तो हमारी ट्राइंगल के वर्टिसेस जो हैं उन तीनों में से कोई एक वर्टेक्स जो है उसको भी अगर आप इस इक्वेशन में यूज कर लें उसकी वैल्यूज, तो दैट शुड सेटिस्फाई दिस इक्वेशन. The set of all points x, y, z that solve the equation is exactly all the points that lie in the plane. Now let's take a look at some of the examples of planes. We have 2 examples. The first has the normal pointing away from the origin, which causes the distance d to be negative. We can try some sample values if we feel like, but let's take a look at this picture first. In this case, the normal is sticking out of the surface of the plane, and distance D is negative because the normal is pointed away from the origin. So whenever we have this kind of a case, the distance D of that plane would be known to be negative length. So हम मुझे कहेंगे उसकी लेंथ जो है वो minus D है because it is away from the origin. The normal is pointing away from the origin. The second example is when we have the normal pointing towards the origin. So D is positive in that case. Of course, if the plane goes through the origin, D is got to be 0, as we have already discussed, because the distance from the origin to that plane would eventually be virtually be 0, because the plane would be passing through origin rather than staying away from it. So now we know that if we have a plane whose normal is sticking out of its surface and is pointing away from the origin, then distance D would be negative. And if the normal is pointing towards the origin, then for such a plane, distance D would be positive. And this is the second example. Take a look at the picture. We are looking at a plane whose normal is pointing towards the origin, and here we say that the length is positive, D is a positive value. Normal away from origin, D negative. Normal towards the origin, D positive. Now it is important to notice that technically the normal xyz does not have to be a unit length for it to be a valid plane equation, but the problem is that if we have this as a unit length, then it is going to make life easy for us. So things really turn out to be nicer if we have a unit length vector. Therefore, we typically would be using unit length. Next is the idea of constructing a plane. We can make use of the concept of three vertices that define a triangle to be used to come up with the definition of a plane. We can construct a plane using 3 points, and this is what we are going to do right now. We'll try to establish the concept of defining or describing a plane with the help of 3 points. जब हमने ये कहा कि triangle by definition has to exist in a single plane, तो उसके पीछे रीज़न ये थी कि उसके अंदर सिर्फ 3 पॉइंट्स हैं जिनको अगर हम स्ट्रेट लाइंस के जरिए से मिलाते हैं तो आप ये देखिए all those will have to coexist in the same plane as opposed to another picture जिसके अंदर अगर हमारे पास 4 vertices हों जिनको हमने मिला के पिक्चर बनानी हो, no matter what the shape may be, but we do have the option of placing that 4th point in such a manner in our 3-dimensional space that we end up having some picture, some figure which is not accommodatable in an infinitely thin slice of 3D space. Very, very easy. You draw a triangle maybe on some paper. The 4th point, you can put it somewhere up there in the air. And if you need to join any of the points with that 4th point, those would not be existing on the same paper. So जो हमने example भी ली थी शुरू में कि अगर हम प्लेन को एज्यूम करना चाहें तो वो एक लार्ज पीस ऑफ पेपर है, so उसको भी सामने रखते हुए हम ये कॉन्सेप्चुअली बात आसानी से समझ सकते हैं. So any triangle or any figure that is made on that surface, that is part of the plane that we are talking about. But अगर हमारे पास चौथा पॉइंट आ जाए तो चौथे पॉइंट के पास की हमारे पास ऑप्शन मौजूद है कि we can put it elsewhere. अगर उन्हीं में से आप उसी पेपर के वाले तीनों पॉइंट्स की बात कर रहे हैं और कहेंगे हम 2 को रख लेते हैं उसी पेपर के ऊपर और जो तीसरा पॉइंट है उसको कहीं हवा में ले जाते हैं, तो एक्चुअली आप कर क्या रहे होंगे, आप एक नया प्लेन डिफाइन कर रहे होंगे. बिकॉज नाउ द थर्ड पॉइंट वुड नो मोर बी ऑन दैट पीस ऑफ पेपर, दैट वुड बी in the air, which actually in effect would again be defining another plane oriented at a different angle. No problems with that. That is the key to this division of surfaces into multiple triangles existing in multiple different planes. We just perform a cross product between the two vectors made up by the 3 points. That's the basic idea lying behind the making of or defining of a plane using 3 points. तीनों पॉइंट्स या तीनों वर्टिसेस जो कि टिपिकली हम बात करते आ रहे हैं ट्राइंगल के हवाले से, तो उसके तीनों वर्टिसेस जो कि डिफाइन करते हैं ट्राइंगल को, उन तीनों पॉइंट्स को इस्तेमाल करते हुए हम 2 वेक्टर्स डिफाइन करेंगे और उन 2 वेक्टर्स के प्रोडक्ट के जरिए से, क्रॉस प्रोडक्ट के जरिए से, विल बी एबल टू come up with this idea of the plane. In the picture on the screen right now, you can see the points P1, P2 and P3, which effectively are drawing a triangle or defining a triangle, they are coexisting in a plane. The normal to the plane is perpendicular to each of the edges of this triangle. So if we see P1, P2 or P2, P3, the given normal, which is extended out of this plane surface, is normal or perpendicular to all the two, the P1, P2 edge and the P2, P3 edge. So we say that the normal is equal to P1 minus P2 cross P3 minus P2, and K is equal to normal times P1. Now given that, please note that it is extremely important to keep track of which direction your points are stored in. Let's take 3 points stored in clockwise direction in the XY plane. We have already talked about storing vertices of triangles in a clockwise winding manner or in anti-clockwise manner. We have been only discussing the clockwise order as yet. So take a look at this picture. So if you have P1 as 0, 0, 0, P2 as 0, 1, 0, and P3 as 1, 0, 0, the normal to the plane of these 3 points, that can be defined as P1 minus P2 cross P3 minus P2. Now making use of the actual values, we'll be able to come up with 0, minus 1, 0 crossed with 1, minus 1, 0, and this would actually result in minus 1 times 0 minus 0 times minus 1. The second one would be 0 times 1 minus 0 times 0, and the third coordinate would be 0 times minus 1 minus minus 1 times 1, and that boils down to the point 0, 0, 1, and that would actually be defining the normal. Now the z-axis, if we were to store the points counterclockwise, the normal calculated would be 0, 0, minus 1, which is still the z-axis, but in the opposite direction. It's important to keep track of these things, since we often need these things and planes equations to be correct in the order to determine which side of the polygon an object such as the viewpoint is on. Very, very critically looking at this, if we have an object defined in one plane, the point of view or the camera from where we are looking at that scene, shall it be able to see those objects or not, becomes very important. Because as I said earlier, in graphics, in three-dimensional graphics, we will be having certain objects which would be behind certain other objects, or certain surfaces which would be behind certain other surfaces, and hence would not be visible. So in order to establish this fact that whatever object we are talking about on a specific plane is actually visible and must be drawn as part of the scene, is very important. And we will have to establish this, and we do have mathematics to help us calculate that, and we'll be making use of those calculations in order to establish the fact that, okay, in this plane, whatever part of the surface is being defined as a strip of triangles or a triangle is visible or is not visible. The following illustration is going to explain that. So the basic idea of construction of a plane has been discussed, and now we can go into the specific details of constructing a plane from 3 points on the plane. Normal vector n is equal to the cross product b minus a comma c minus a. The normalization of n would be the next part, in which we said that we will be finding a unit vector, because we have already seen in our calculations that unit vector always helps. D is equal to minus dot product of n comma a. Now we have got the normal and we've got some point on the plane, and given these two, if we want to define a plane, how would that go? Just take a look at your screen. Normalize n, which is the finding a unit vector, then d is equal to minus dot product of n comma a. and that's about it. Next thing that we talk about is locality, a definition of locality with reference to a plane. Now this is important because, as we have discussed earlier on as well, that we are concerned with what part of a surface of an object is visible and what part is not visible or is hidden. Similarly, we would like to know what point or what part of object is which part of which plane, or if we are talking about a specific plane, where a specific point exists. Is it on that plane or is it away from it? If it is away, then where? Is it in front of it or is it behind it? So these things will require certain calculations to be performed in order to get established. So we have this facility that we will be able to calculate the locality of any given point. It is one of the most important operations that planes allow us or let us do. That is, for any given point, we can calculate whether that point is existing as part of the plane, as part of all the points that are forming that plane, coplanar with all of them, or is in front of it, or is behind it, as I said. Very simple calculation that we need to make. We already know the equation of the plane, ax plus by plus cz plus d. For that very point that we are interested in finding out the locality of, we can use the same equation, put the xyz coordinates in the equation, and if it evaluates perfectly fine, comes out to be equal to 0, we know that the given point is got to be part of the plane. और अगर ऐसा हो कि हम point की values डालें उसमें, calculation results in a positive value, a non-zero positive value, that means it is going to be a point in front of the plane. और अगर ये evaluation result करे एक negative value में, तो इसका मतलब ये होगा कि ये point behind that plane. So for a moment, if we believe that the very plane that we are talking about is the view plane, जो कुछ उसके अंदर आ रहा है सिर्फ हमने वो दिखाना है और उसके पीछे वाली चीज़ों को हमने omit कर देना है, तो फिर जो भी representative reference points होंगे उनको हम इस प्लेन की इक्वेशन के अंदर डाल के इवेल्युएशन करके देख लेंगे. अगर हमारा रिजल्टेंट 0 आ रहा होगा तो इसका मतलब यह है कि वो चीज़ें हैं जो कि उस प्लेन पर एग्जिस्ट कर रही हैं, और अगर वैल्यू पॉजिटिव आ रही होगी तो इसका मतलब है कि इन फ्रंट ऑफ दैट प्लेन एग्जिस्ट कर रही हैं. इन फ्रंट ऑफ दैट प्लेन का मतलब ये होता है कि जिस तरफ से हम व्यू कर रहे हैं, जिस तरफ कैमरा देख रहा है, जिस तरफ से सीन को, उस तरफ एग्जिस्ट कर रही हैं. देयरफॉर एनीथिंग दैट कम्स बिटवीन द कैमरा एंड दैट प्लेन, दैट वुड बी विजिबल. We have already talked about the concept of the frustum. So giving all those exceptions their room, whenever required, we will be talking about that near and the far clipping concepts. But in general, जो चीज़ें प्लेन पर एग्जिस्ट करती हैं वो दिखाई दे रही होंगी, जो उस प्लेन के फ्रंट पे हैं वो नज़र आ रही होंगी, एंड एनीथिंग बिहाइंड दैट प्लेन, इफ दैट इज टू बी हिडन, वी कैन ऑलवेज डिस्टिंग्विश दैट. जिसके लिए वैल्यू नेगेटिव इवैल्यूएट होकर आ जाएगी, इसका मतलब यह है कि वो प्लेन के पीछे है and therefore would not be visible. You can take a look at this illustration where we have a plane, the normal sticking out of it, 1, 0, 0 unit vector is poised at distance -5, and any points that satisfy this plane would actually be, plane equation would be part of the plane. And for those that we have values evaluated to be positive, as is for the vector on the right hand side, you find that the equation evaluates to +2, and the point is in front of the plane. And for any points that the value evaluates to a -1, as in the case of the left one, -2.5, that exists or resides behind the plane. So depending upon how we make decision of which points to display and which not to, we'll be able to distinguish at least the locality of those points, if they exist in the plane or they exist in front of it or behind it. Next topic is the backface culling, which is actually the related topic, related concept, that how we shall be able to distinguish and define the faces that are on the back of an object and hence must be kept hidden and must not be drawn, must not be shown. So this is done making use of the very concepts that we have already just discussed. If we can do it for a point, we should be able to do it for any polygon. अगर हमने अभी locality of a point डिस्क्राइब कर ली है, उसको डिफाइन कर लिया है, स्पेसिफाई कर लिया है कि किसी भी प्लेन के अंदर एग्जिस्ट करने वाले पॉइंट को, उसके सामने एग्जिस्ट करने वाले पॉइंट को या उसके पीछे एग्जिस्ट करने वाले पॉइंट को हम किस तरह से डिस्टिंग्विश कर सकते हैं. इफ वी कैन डू इट फॉर अ पॉइंट, वी कैन डू इट फॉर द पॉलीगॉन. पॉलीगॉन क्या है? मल्टीपल वर्टिसेस की कलेक्शन ही से बनती है ना. तो अगर वो तमाम वर्टिसेस को हम एज इंडिविजुअल पॉइंट्स ट्रीट करना शुरू कर दें तो वी शुड बी एबल टू एस्टैब्लिश द सेम फैक्ट फॉर ऑल ऑफ दोज पॉइंट्स. राइट? आपके पास एक पेंटागन है, यू गॉट 5 पॉइंट्स, ठीक है, उनके जरिए से मिलकर बनी है. अब हर एक पॉइंट को आप अलग अलग ट्रीट कर लीजिए यूजिंग द इक्वेशन ऑफ द प्लेन दैट इज बीइंग कंसिडर्ड. विल बी एबल टू एस्टैब्लिश कि क्या वो पांचों के पांचों पॉइंट उसी प्लेन के ऊपर एग्जिस्ट कर रहे हैं या पांचों के पांचों फ्रंट पे आ रहे हैं या बैक पे आ रहे हैं. ठीक है ना? लेकिन एक एक्सेप्शन भी हो सकती है, एंड दैट इज कि अगर हमारे पास ये 5 पॉइंट्स की हम बात कर रहे हैं, 5, 7, 6 कुछ भी हो सकते हैं, तो इनमें से कुछ पॉइंट फ्रंट पे हों, कुछ बैक पे हों. द प्लेन दैट वी आर कंसिडरिंग देम फॉर, मुमकिन है कि उसके ऊपर सारे के सारे लाई ना करते हों, सारे के सारे उसके फ्रंट पे या सारे के सारे उसके बैक पे लाई ना करते हों. तो ये एक और डिफरेंट केस भी हो सकता है जिसके अंदर कुछ तो पॉइंट्स ऐसे हों जो फ्रंट पे आ रहे हैं और कुछ बैक पे आ रहे हों. बट वी शुड बी एबल टू टेल वेन एवर दैट हैपन्स, एंड वी विल बी एबल टू टेल बिकॉज हर एक पॉइंट को हम इंडिविजुअली प्लेन की इक्वेशन के साथ टेस्ट कर सकते हैं. टू परफॉर्म द बैक फेस स्कल, जस्ट सब्ट्रैक्ट वन ऑफ द ट्राइंगल्स पॉइंट्स फ्रॉम द कैमरा लोकेशन and perform a dot product with the resultant vector and the normal. If the result of the dot product is greater than 0, then the viewpoint was in front of the triangle. Look at this illustration. So we've got the vertex 0, 1 and 2. The viewer is the point where the camera would be, the vector extending from that viewpoint to the vertex, and the normal to our triangle. If we perform a dot product of the two and that turns out to be greater than 0, we know it is in front of the plane. If it turns out to be lesser than 0, we know it is where? Behind the plane. If it turns out to be equal to 0, that means it is going to be perpendicular. The two are perpendicular to each other. That means that can only be perpendicular if the point exists in the plane. So if the point is in the plane, if it is in front of the plane, or if it is behind the plane, all three cases would be distinguished and dealt with. And that's how we'll be able to perform the back face culling. But the exception that we talked about, वो क्या सूरत थी जिसके अंदर हमने ये कहा था कि सारे के सारे फ्रंट पे या सारे के सारे पॉइंट बैक पे ना हो, कुछ फ्रंट पे और कुछ बैक पे आ जाएं, तो उस सूरत में फिर हमारा काम थोड़ा सा मुश्किल हो जाता है. What we'll have to do is we will have to perform certain tests for testing intersection between line and plane, because उस सूरत में जो पॉलीगॉन के एजेस होंगे, those would be lines that would be intersecting that plane. They would be being through it, because अगर कुछ पॉइंट पीछे हैं और कुछ फ्रंट पे हैं तो इसका मतलब यह है कि उनको मिलाने वाली जो लाइन सेगमेंट्स हैं, they would be crossing this plane, and since they would be crossing the plane, there's got to be the points of intersection of those lines with the plane. Now this occurs at the point which satisfies both the line and the plane equations, and that is the point of interest which would be calculated now. Now using the line equation, we have P is equal to org plus U times dir. The plane equation, we already know, P times normal minus K equals 0. Let's mark these two, the line equation and the plane equation, and substituting value from 1 into 2, that would be for P, we are going to get some results like this. Org plus U times dir, that would take the place of P, times normal minus K equals 0. Now this can be rearranged as U times direction times normal is equal to K minus org times normal. And this can further be rearranged to have it written as u equals k minus org times normal divided by dir times normal. Now, if d times normal equals 0, then the line runs parallel to the plane and no intersection occurs. Getting it? If d times normal evaluates to be equal to 0, then that means that the line is running parallel to the plane and they are not intersecting with each other. The exact point at which intersection does occur can be found by plugging the value of parameter u back into the line equation in 1. We'll be making use of the line equation 1 to incorporate this u value, and if we are able to find a non-zero value, we would be able to tell that, of course, they are intersecting with each other. And this would be the point that would be used to decide what part of that polygon is to be displayed or kept visible and what part is to be kept hidden. So, today we have talked about the triangles and the planes. It was an interesting discussion because we have talked about surfaces of 3D objects decomposed into multiple triangles, and then the fact that every triangle is living in its own plane, that is also giving us some room for playing the way we were playing in 2D graphics. So if we need to fill up the surface of any given three-dimensional object and we have subdivided into multiple triangles, each of those triangles can be dealt with the way we were dealing with two-dimensional triangles, and we can fill them accordingly. We do know multiple filling algorithms for that matter. So we'll be making use of these concepts and stretching them a little further to come up with some more exciting ideas about three-dimensional graphics next time. So folks, I hope you would have enjoyed our journey today, another step into it. We have covered up to the concept of planes and triangles, but still we have a lot more to cover before we can walk into realistic three-dimensional modeling and rendering of objects. But this is going to be discussed in our coming lectures, inshallah. So I hope you'll stay with me and we'll be getting together again next time, inshallah. तब तक के लिए इजाज़त दीजिएगा. फ़ी अमान अल्लाह.